Ramanan, we start. Morning. All right. I hope everybody is fine and well. In our previous class, we started the OSI layers, the 7 days that we're going to study for the rest of the course. And from the first layer that we saw is the physical layer. And we took the physical layer functions, in which we saw most of the functions that is related to the physical layer with regards to the physical transmission of the raw bits, that is zeros and ones. Now to continue with that, today we'll go more into details about the physical layer. I will share with you a page in which there would be the 7 layers. I've taken a picture of it. I think I can just put it in the Google Classroom. Before that, let me first continue with the physical layer examples as well. I'll switch off the video and I will use the board. All right, I have the transmission media here for PPT. I would use that also, and I would want a whiteboard as well. I'll see whether I can switch between the two. Ramanan, now it's whiteboard. Okay. I'll first write physical layer examples. What we discussed in the previous class, it was what physical layer functions are. Okay. So we understood some interfaces that come in between the wire and the host. We also saw the applications with respect to modulation. We saw what physical layer does with respect to multiplexing, carrier sensing, line coding, whether it's point-to-point link, multi-point, and so on. We saw physical topology. When we talk about bus, ring, mesh, star, and so on, we are talking about the physical layer. Also, we saw serial parallel communication. This is the physical layer. Simplex, half duplex, full duplex, this again is taken care by the physical layer. Now, those were the functions. Now we see the examples of physical layer. If you remember, some time back, we used to have modems for telephone lines. So they are the example. The first one that I'll take, telephone network modem. They used to be known as V.92. That is the example that we have. The infrared IDA physical layer. This is another example. USB physical layer. This is another examples. Ethernet, which we are going to discuss as well. Ethernet has several, types. So Ethernet has its own physical layer for various types, including 10 base T, 10 base 5, and so on, 100 base T, 1000 base T, 100 base X, 1000 base SX, and so on, other varieties. I'll come to that also, what are those types. As of now, let's see this. DSL, what we know as digital subscriber line. ISDN, which is full form for integrated services digital network. SONET, SDH, SONET for synchronous optical network, and SDH for synchronous digital hierarchy. So other things also, like for example, Bluetooth physical layer, GSM, Very nothing is visible. How about you, uh, Ramanand? Okay, Marian, it might take some time to get displayed. So whatever is displayed, it's clear? Okay, okay, fine. So these are some of the examples. Like I said, Firewire, TransferJet. If you just Google them, you can see how they actually look like. Let me see. I can show picture of Firewire. Let me. You see what I'm sharing, or is still the whiteboard? Now, okay. So this is the example of a Firewire port. Okay, we used to have a Firewire cable, and another example just now I said was for TransferJet. Okay, like this one we used to have a port to transfer like pictures and so on. These are the examples that we have. Let me go back. Go back. Okay. Now, these are some of the examples that we see with respect to the physical layer. Now, some other hardware that you see with, I'll just write that also as hardware examples, hardware equipment that you see with respect to the physical layer is a repeater. Now, what is a repeater? Nowadays, you do not generally see a repeater. Why? Because its work has been taken up by switches and hubs. By repeater, the name itself says it repeats something. It so happens that if you use a certain type of wire, let's say Cat6 wire, its maximum distance that it can transmit a signal is, let's say, 100 meters. Now, what happens if you are connecting two hostels? It's more than 100 meters. If you use, let's say, 150 meters, after 100 meters, the signal wouldn't happen. Obviously, you will not get the data from the other side. So in between, you would use a device, right? Can be an active device or a passive device, in which typically an active device, which would be powered so that it takes the incoming signal, regenerates it, and transmits it. So if you have a distance of 200, in the middle, you just put it there, a repeater, and it will regenerate the signal. This is an example of the hardware equipment that we have. There used to be passive hubs also. Nowadays, you do not see these hubs because they have been again taken up by the uh, what you call switches. Modem is another example of this. And we have IO devices. What are these IO devices? It's like when the fiber optic cable is being terminated in the switch, you need a converter. We call that as fiber media converter What does it convert? It basically converts light into electrical impulse and electrical impulse into light, the other way around as well. When I say you do not see some of these devices here, repeater and so on, because their functionality has been taken over by other devices. Now, in case nowadays you think of extending your LANs and so on, you use a hub. Hub is powered and then it can also repeat the signal. So repeater is itself inside the switch that you would be using for, let's say, gaming and so on. Then we have connectors. With respect to connectors, how do you, now you have a host, another host, you have a wire in between. We'll come to wires in today's class as well and see what are guided and unguided media. There are different types of connectors which are used to connect them. The typical cable that you use is UTP, and the connector that you use for it is RJ45, where RJ stands for register jack. If you use coaxial cable, again in today's class we'll get to know what these cables are. We have BNC, BNC-T, and also we have BNC terminator. Now, if you have seen the bus, if you had seen the bus topology, wherein we had a link here, okay, and then on it we had different devices connected to it, like this. What you typically use RJ45 and so on. But keeping in mind that for bus we would need some connector here, which is a T-shaped connector. Here we use BNC connectors, which is bayonet Neal connector. Again, you can just Google it and see how this connector actually looks like. A T-shaped connector here, a T-shaped connector. Then there is BNC terminator as well. This would be used at the two ends here, which would terminate the bus, so that electrical impulse doesn't keep on moving. The next we see is fiber. Fiber has its own connectors as well. We have SC connector, ST connector, and so on. I just now mentioned that fiber media connectors, the IO devices that we use for fiber to convert the signal into light and back. So in short, after this connector, there are wires. There is other things that we are going to take just now. Keep in mind, if I'm talking about cables, I'm talking about physical layer. If I'm talking about connectors, I'm talking about physical layer. If I'm talking about transmitters, TX, RX, transmitters and receivers that we have for wireless, this is part of the physical layer. Multiplexers, again, this is part of the physical layer. Transceivers and couplers as well. Couplers, a couple is defined as the amount of EM power that we have within the line. This is part of the physical layer. Now let's move to the transmission media. For this, let me just close this whiteboard. Let me go back to the Someone, can you see this? Transmission media? Okay, transmission media. Okay, fine. Can I write on this? Can you try writing on it? Anybody? Okay, yeah, I got it. I got it. I got it. So basically, transmission media, what is transmission media? There are various physical media that help us in sending the bits from one end to another end. How do we choose a transmission media? Arifa, are you able to see? Okay, fine. Now, how do you choose this transmission media? Based on the cost, based on installation where you have to install, its bandwidth, the delays, and so on. This defines how you would choose a transmission medium, how fast you want the data, how is the terrain, can you put this and so on. You have one as guided and another as unguided transmission media. Wherein guided means you use a physical link, unguided means you use a wireless link. Change page now. So here it's written based on what we are actually using it. It's based on bandwidth, transmission impairments. I'm coming to that within this class as well, interference. Then receivers that we require in between. So here is the guided transmission media. The first one is the twisted pair. The second one is the coaxial cable. And the third one is the optical fiber. What is twisted pair? As is visible here within this picture, that twisted pair, one of the oldest and still commonly used communication mechanism. Have you seen this? I think most of you would have seen it. Where your telephone line, which is a single pair twisted, cable, in which there are two lines here. You can see one black and one white. One of the line is used for signal. Another is for ground reference. The receiver uses the difference between the two signals to find out the signal that is being transmitted. Inside it, there is an insulated copper wire, which is a very small copper wire, typically of the dimension of 1 millimeter between in both of these. Now, these two wires are twisted together, form a in a helical manner. You know, helical manner, you might have heard this like DNA helix. That is the twists that you have here. Now, why are these twists made here? Twists are made to reduce the electrical interference from what? From a close by pair. Now, sometimes it happens, you are on your landline. It used to happen before, and you used to hear radio there. Haven't you heard that? I think most of you would have heard that radio playing in your telephone. Now, this is because the twisting may not be right. There may be interference from nearby pairs. Uh, Twisting helps in noise rejection. Sometimes it's a parallel wire, two parallel wires, and these two parallel wires can constitute what we know as a simple antenna, and that's why you hear these radio going on. The good thing about this twisted pair is that it used to run several kilometers without actually amplification. Now, if you needed to amplify this, what you had to do, a repeater has to be used in order to amplify it. Common application, I said, is telephone. It was used for analog previously. Nowadays, it's used for digital communication as well. How much it could carry, the bandwidth here used to be dependent upon the thickness of the wire as well as how far the distance the wire is traveling. It can, communicate several megabits for few kilometers. The good thing about the twisted pair is cheap, easy to work with, low data rate, but I mean, these are the cons of it: low data rate and short range. This is what I just now explained about the crosstalk. And these are its categories. There is category 3, twisted pair. This is 2 insulated wires. This is for the telephone that has been used, Cat 6. Then you see Cat 4 as well, Cat 5 as well. You can see the differences between these is the frequencies that has been used, the twist lengths, how many twists have you per centimeter. The more the number of twists, the better the wire, and so on. Now, then came the category 5 as well. Like I said, what's the difference between 4 and 5? 5 had more twists per centimeter. 5 had Teflon insulation. It had lesser crosstalk. It had, obviously, with all these things, it had better quality signal over a longer distance. It was used for high-speed computer communication. All of these are referred to as UTP, which is unshielded twisted pair. Cat 3, Cat 4, Cat 5. Now the maximum specified distances of these twisted pair for transmission of data is 100 meters. Cat 5, what you see, Cat 5 is of 4 pairs. That means 8 wires going on. This is the connector that we use for it. Ramanan, can you see? So there is a connector R45 written there. Yes, twisted pair. Here, let me see if I can annotation here. Okay, this one. Right? Okay. So this is the connector that we use. This was our lab first, which we couldn't do, but hopefully we'll do it, in which we use 8 wires to position within these pin positions of 8. The patch cord that you use, the cross wire or the straight wire, is made up of this wire and the connector RJ45 that we have here. The improvement of this Cat 5 was Cat 6 cable. Now we have Cat 6E as well, in which we have better transmission speeds. Okay. This connector RJ45 is also known as 8P8C modular connector. 8 pair, 8 connector modular connector, 8P8C. Now I was talking about Cat 6. It's used for gigabit Ethernet channels, which are much faster, and it has less crosstalk and lesser system noise as well. This is the comparison sheet of the shielded and unshielded twisted pair. We won't go into the depth here, we'll just move on. And this is what category of UTP is used for what technology of Ethernet, and also what is the speed of each category. Now moving on to the next one, that is the coaxial cable. So we had baseband coaxial cable, we had broadband coaxial cable. Let's see if I can annotate here. Baseband coaxial cable and broadband coaxial cable. In both of them are known as coax in short, for coaxial cable. It has a better shielding than the twisted pair. When we talk about this, let me see if there's an image of it. No, it's no image there. Okay. Now, how does it look like? I'll share another file to see if we have the image of these. Yeah. No, I wasn't looking for a good image of it. Anyhow, it's not here. Let me just go back. Now, coaxial cable was for longer distances with higher speeds. The two types that we had for baseband coaxial cable are, one is RG5811 and another is RG59. The two types have the difference of uh, whether this one is used for digital communication or whether it is used for the analog communication. RJ5811, this was used for, this one was used for, this is 50 ohm used for digital communication, and the second one is 75 ohm, which is used for analog communication. What it has in the middle there is a stiff copper wire. I'll try to draw the figure here. This is the center of it, which is the stiff copper wire. Then after this, there is a surrounding of another layer. This is what we call as an insulating material, like this over it. Over it, we have a cylindrical mesh, which is another conductor here. I would use this one here. Like this. It's a mesh. A mesh here. Okay. And over it is another protective layer, which is known as the plastic sheet. This is typical, cable that comes to your home. This is what we have. Okay. All right. Uh, the cable connection that comes to your home has a stiff core, insulating material, then a mesh, and then over it. Going back, it can go for a kilometer, the data rate of 1 to 2 Gbps. And this is the cable that would have the BNC connectors that I talked about just now. The bayonet nail concealment connector, BNC connectors. The connectors, they look like this. I'll show you one example here. This is the example of BNC connector, a T shape. Okay. There is an example of BNC terminator as well. How do they actually terminate it? At the end of the wire, you have something like this. This is easy to stuff. Okay, then this uh, anyhow, these are the connectors, the BNC connectors that we come across. The second one that we come across is the broadband coaxial cable. Analog transmission used to be, for standard cable TV. Nowadays, that is digital. Broadband, which was used nowadays in telephone, which has frequency wider than 4 kilohertz. It also uses the same type of coaxial cable. Now I'll move on to the next one. That is the optical fiber. We all are aware of this type of transmission media in which light is used to transmit the electrical impulse. You can imagine the ARPANET, the grandfather network that we discussed about, used 56 kilobits per second for data communication. And from there, we are this time talking about many gigabits per second. That is the modern optical communication. And also, we not only improved with respect to the speed of communication that I'm talking about, multiple gigabits. We also improved with respect to the distance of transmission. You have these fibers laid across, underneath the sea, in sea trenches for several hundred kilometers together without the use of a repeater. And also, with respect to the error rate we had previously of 10 to the power of -5 per bit to almost zero in fiber optics. Now, current fiber optic can give you a speed of 50 Tbps per second, 50,000 Gbps. But then why are we talking about 110, only few Gbps, if we can communicate at the rate of 50 Gbps? Can anybody answer this? You can use your microphone, you can type in whichever. Did you get my question? Okay, I repeat. The current optical fiber technology can give us more than 50 Tbps, that is 50,000 gigabits per second. But we still talk about 1 Gbps, 10 Gbps, and so on. Why is it so? Anybody? No? Okay, the reason for this is because the inability, we have an inability to convert electrical signal to this optical signal at this faster rate. The maximum we can convert the fast, that's why we talk about 1 Gbps and 10 Gbps. So this is the bottleneck that we have, the input output, the IOs that we have, the converters of light to electrical impulse and electrical impulse to light. Right, Abhishek, it's not about costly. Cost is not a factor. It's about our self devices don't support. Because your answer is right, it doesn't support, but it's not just because it's about support. It's about we. I mean, if you mean to say that our conversion is not that faster, if you mean that is the support, yes, you're right. That we cannot convert it so fast. Well, there are, Enquist and Shannon limits which are imposed, which you would have studied in your digital communication. Those limitations are not in fiber. That's a good part of it. Error is less. And how does it actually work? Optical transmission has three main components. The first component that we come across is the light source. The second component that we have is transmission medium, that is the fiber that we have. And the third component that we have is detector. Light source is basically mhm. Okay. Right. Right. Coming back. Now we are discussing about the optical transmission, this optical fiber transmission, in which there are three components. The first one being the light source, the second one being the transmission medium, and the third one being the detector. I need to admit the people who come late here that pauses this thing stuff. Yes, you better be there on time. Raman, take the attendance. Now, how is this ones and zeros sent? Typically, ones and zeros are like pulse of light is one, absence of light is zero. What is this transmission medium? It's a very thin, we call it as ultra thin fiber of glass. And the light source creates the light and then transmission through this optical fiber, and the detector, when the light falls on the detector, it detects it and says this is the one, converts that into an electrical pulse once the light has fallen on it. Now you understand here in the picture that is given here, the optical fiber, how it looks like. There is a central core, there is a cladding, and there is a jacket. Glass is the core. The cladding that we have here, covers this glass, and then we have the jacket. Now, why you have this cladding here? When light passes from one medium to another, it is refracted. What is refraction? Bending of light. Might have studied in physics. Amount of refraction depends upon the two media, the refraction indices. Actually, the properties of two media, how much it will bend, depend upon the property of the two media. But for certain angle of incidences which are above a certain critical value, the light is refracted back into the medium. Thus, our cladding is chosen, the cladding that is shown here is chosen in such a way that we get reflection within it. This is how the light at less than the critical angle is absorbed in the jacket, which is shown in the picture, and the light transmits in this way. This is known as total internal reflection. So the light ray here, which is incident or above the critical angle, is trapped inside the fiber, and thus it can propagate for many, many kilometers with actually or with virtually no loss. And we can have different rays bouncing around at different angles. And if we can pass many rays within the same fiber, you know, each ray would have a different angle. What we call as each ray would have a different mode. So we'll call this as a multi-mode fiber. Another thing is, here you can see the fiber's thickness. Now reduce the fiber's thickness in such a way that it is smaller than this. So see this is, now once you have an electrical pulse moving through it, it will again transmit with this total internal reflection. But the angles are such that the wire is thin such that this would seem that light is traveling in a straight direction. Can you see the picture here, Ramanan, that I have drawn about the optical fiber? Is that visible? Yes, yes. What I mean by these three straight lines is I have reduced the diameter here, the one which had shown the angles here on the picture. I have reduced the diameter of the fiber in so much so that the wavelength of light reduced to a few wavelengths of light, and the fiber would act like a straight line, a waveguide. So light can here propagate in a straight line without bouncing at the edges. The fiber is so thin. And if this type of fiber is used, we call this as single mode fiber. This one is the example of single mode fiber. Now visible, Arifa, or still taking time? Okay. Now this is expensive, but you can see that it is good for longer distance communication. You can have several gigabits over 30 kilometers. What and light sources here, we would need powerful lasers. Some powerful lasers can drive up to hundreds of kilometers without actually need of repeaters. I hope this is clear. Basically, optical fiber is about glass, a very thin clear glass. In fact, it is possible to send these pulses of light, dispersed in such a way in a spatial shape for thousands of kilometers. Those pulses are known as solitons. Okay, I won't go there much. Fiber optic has a core typically which is very small, which is 50 microns in diameter. To understand 50 microns in diameter, your hair is 50 microns. So you can understand how thick it is. But then you will say that, sir, we see a fiber moving across our department that is thick. The core is of 50 microns. Then you have cladding and jacket to protect it. That makes it a bit thicker. And also, if you talk about single mode fiber, which I have drawn here, its core is much lesser than our strand of hair. That is of the order of 8 to 10 microns. Normally, fibers are laid within the ground. Uh, typically, you dig 1 meters down and then you place in the fiber. In fact, when you pass the fiber through the sea as well, what we call as transoceanic fiber, they are buried in trenches under the sea. You dig it with machines under the sea as well and lay those fibers. That's why at some places, in fact, just in front of computer center, there is a small milestone shaped, I'll say it just looks like a milestone on which it is written BSNL fiber or like geo fiber, which denotes that here under this there is a fiber moving across at a depth of around 1 meters. in case you are digging or doing something, please ensure that you take care of that. We would have seen the possible joining, splitting of fiber also in the lab. So once we take about UTP and crimping and all, we'll try to have this also demonstrated there. How are fibers basically connected? They can be terminated in connectors, they can be plugged together in fiber sockets. But the problem with those fiber sockets are that they lose 10 to 20% of light. Then what do you actually do? You do splicing of fiber. We call them, when you have to connect these, you call them splicing. We use, mechanical splicers in which two fibers are carefully put together, and then you put a clamp over them. Around 10% of loss is there. And the third, the best way to do is to join or melt it or fuse the together to form, it looks like a single good connection with almost, no attenuation, with almost no loss. So obviously among all of these, fibers can handle much better bandwidth than copper. It is good, but it is costly. The good thing about fiber is that since it doesn't use electrical impulses, it uses light impulse, which means interference is also less. What interference I mean? I mean interference because of electromagnetic interference, power, machines nearby, and so on. Those cannot interfere. It's glass. Glass doesn't corrode, whereas other way we are using copper wires and otherwise which would corrode with time. And also important aspect of using fiber is that uh, you know tappers cannot be there. Oh, okay, Vikas has asked a question that if optical fiber core is glass, how can it so easily bend? Several reasons for it is that the fiber inside is so small, okay, that it can easily bend. If you have a book with you, okay, this time, bend the book. How difficult it is. You cannot bend it, right? Now take one page of that book and try to bend it. You can easily bend it. This is the example why you can easily bend it. Now why doesn't it break? That is the other point in which if you know you have a cladding, if you have a jacket, see your hair and then actually see the fiber that you see moving around. It's very thick compared to that. So a lot of protection is there, which makes it safe as well as it can bend. Now, coming back to, I hope that answers Vikas. Coming back to the security, I was saying that the fiber is secure compared to other one because we do not have wire tappers here. What I mean wire tapper, on other channels, other wires, you can have other people connecting to it, and it's like, in telephone, other one connects and listens to what you're speaking. That can happen in digital transmission as well, in which tapping can be done. But you cannot break this optical fiber and listen to it. It's not easy to do that because obviously it would have a lot of loss and you cannot transmit data with loss in the fiber. These were the three medias that we discussed. And next thing that we have, this is the optical fiber application. When you talk about trunks, I have given you in an earlier class what we meant by the trunks. Here is about types of these optical fibers: step indexed, graded indexed, multimode, and so on. Next is the unguided transmission. Unguided transmission is basically wireless transmission. the history of wireless transmission when it began in Hawaiian Island. We can go that to some other time. We're discussing here about the electromagnetic spectrum. Electrons move, they create waves that can propagate through the free space, even through the vacuum. This was predicted by by James Maxwell and then produced by the Heinrich Hertz, which typically you remember as wavelength into frequency equal to constant, lambda f equal to c. Constant was the speed of light. So we go to the spectrum somewhere. Let me see if we don't have a spectrum here, but anyhow, if you see the spectrum here, then you would get to know what frequencies are there, starting from radio, microwave, infrared, visible light, and UV, 10 to the power of 4 to 10 to the power of 16. And among the main band that we use for transmission here, 2 gigahertz to 40 gigahertz, it's about the microwave, highly directional point-to-point and satellite communication. 30 megahertz to 1 gigahertz is omnidirectional and broadcast radio. So basically, we use these frequencies for transmission of data. Mhm. The certain techniques like spread spectrum techniques are used. Most transmissions we use are using the narrow frequency bands to get the best reception. Okay. Now to begin with, we'll briefly go about through these transmissions as well. The first one that we'll cover is radio transmission. The first one is radio transmission. So just a reminder for those who joined late. Okay, now Azish asks a question in which bidirectional communication occur within a single optical fiber, or we need separate fiber. We all right. Okay, coming back, we are discussing. Okay, Izan, you cannot hear, but others can hear. Nawazish. Okay, fine. Okay, Nawazish asks a question here. Nawazish, I'll wait. Nawazish, sir, can bidirectional communication occur with a single optical fiber, or we need separate fiber for each direction? There are different types of fibers. There are simplex fibers, there are duplex fibers as well. There can be one core fiber which can transmit as well as receive data. Means sending and receiving can be done, or I will say bidirectional, or duplex can be within a single data as well. Okay. Yes, it does. That's the answer for your question. Now, how does that basically happen? You use different light impulses to transmit from different directions, different angles. That helps in transmission. Your answer to your question is yes. A single fiber can be a full duplex as well, or bidirectional fiber. Now moving on to the next one, that is the radio transmission. This is the unguided transmission. For those who came late, we are discussing the physical layer. Now in this physical layer, we are taking examples of hardware that we come across, and we came across with the transmission media. There are two types of transmission media, the guided and the unguided. We already took guided, in which we took fiber optics, the twisted pair, the coaxial. Now we are taking the unguided media, in which we are talking about wireless transmission. In wireless transmission, the first one that we have here is radio transmission. Radio transmission, why we used wireless, there are certain places in which it might not be feasible to put on these, like terrain is difficult, a mountainous region. So this provides an ease in the way that you do not have to physically lay the cable across. It's easier to put on these. So it can travel long distances as well. But obviously, as compared to the physical wire, you do not get that much, speeds. And errors are more in wireless communication. Also, radio waves penetrate through buildings easily. So that's why they are widely used for communication. Typical antennas that we use, they are given here: directional, omnidirectional, isotropic antenna is a theoretical point in space. Anyways, let me go back here to omnidirectional antenna. They travel in all directions. So they are the radio waves here are subject to interferences. What kind of interference? Electrical equipment can interfere into radio waves. Motors, for example, they interfere with the radio waves. Also, when it's raining, you see that your transmission is not good because radio waves are absorbed by rain. So interference is a problem. Interference between users is a problem. For radio waves, there is a licensing. Government does the licensing of this radio transmission. We have VLF, LF, and MF bands for radio transmission. Okay. Now, typically, there are ground waves by which radio waves can be sent, or the radio waves can also be transmitted. Let me draw a figure here. Okay. This is the Earth. We have a tower here. We have a tower here. Now, if I use the simple transmission here, one can be transmitted here directly, or there can be waves called as ground waves, or around the earth we know that there is ionosphere. Some waves would get transmitted through these as well, or what we say reflected from ionosphere, and then they reach. We will have ground waves, or we will have, but where here this depicts the earth. So this is the earth's surface that I have. I'll wait for a little while. I think there's a lag from your end. Now, if you can see it now, the center one is the earth. Okay. The first line that I've drawn, the two lines on the two sides are the transmitters. The first line are the ground waves. One is reflected by the ground, another is the direct one. And the third one is touching the ionosphere and getting reflected from the ionosphere. Typically, HF, they bounce off the ionosphere. Ionosphere is the, layer that you see of charged particles around the Earth. height of 100 to 500 kilometers is ionosphere. The next one that we see after radio is this is omnidirectional antenna, that is just parabolic antenna. Again, we won't take this one. Let's go to the next one, that is the satellite microwave transmission. Now, above 100 megahertz, waves travel in straight lines, and these can be narrowly focused. So what you do is basically you concentrate all the energy into a small beam using an antenna. The typical antenna that we use for satellite communication is a parabolic antenna. What is parabolic antenna? The dish shaped. Just next to the old electronics building, there is an antenna that you see, right? That is VSAT terminal, very small aperture terminal. That's for satellite communication of data. We have that working, but its speed is less than half Mbps. Awesome. Now, so these parabolic antennas basically they concentrate all energy into a small beam. Why do we use this microwave? Obviously you can send it to far places. I mean, beyond Earth you are going based on microwave transmission. If you do not have towers visible to each other because of the Earth getting in between the two towers, you would need a repeater to have that radio waves transmitted and so on. Or you have to have higher towers so that you can be away from each other. So we have here a satellite in which a microwave, they do not pass through the buildings well. That's why if you have an example of another parabolic antenna is DTH, direct to home. You use Tata Sky and other dish antennas to get direct to home video transmissions. Now you put them on the walls outside, on the buildings or on the rooftops. Why? Because microwaves do not pass through the buildings well. Even though the beam is very well focused, there is some divergence in space. Some waves get refracted off low-lying atmosphere layers and may not be able to arrive, okay, back to the Earth. There are certain wireless properties that come into effect here. I will just write one of them here as multipath fading occur. Okay, it's like when the waves are sent from one point to another point in microwave, some waves take more time to arrive than the other one. Why? Because they may be refracted off some lower layers, as just now I mentioned. So because of that, the two uh, waves, they come out of phase and they can cancel each other as well. This property is known as multipath fading. So this has effect on our transmission of data as well. Also, microwaves are dependent upon what frequency you are using. They are dependent on weather as well. See, your DTH, Dish TV, when it's raining, it says, sorry, the weather is not good, the transmission is not, the digital transmission won't be possible. Bands up to 10 gigahertz are in use with it, but with 8 gigahertz, above 8 gigahertz, there are problems in absorption by water because of rain and so on. So we use those for microwave. They are not good for communication. Microwaves are good for telephone communication. You have satellite phones. It is for TV distribution and so on. The advantage that you see over the wired media or fiber is that It is very much inexpensive. It is used in typically free bands like ISM band, where ISM stands for industrial, S is scientific, and M is medical bands, free to use. Microwave is also used in cordless telephones, wireless Wi-Fi speakers that you have, security gates, and other short-range communication like you want to open your gate, you can use these microwaves. The next that we have, here's an example of that as well, is infrared. Infrared and millimeter, I believe. Millimeter may not be mentioned here. Okay, let me go back here. Infrared. Infrared is a short range communication. Nowadays, you hardly see infrared. At the most, what you can see is a remote for TV. Okay. Now, they are also going changing into Bluetooth. Why? Because of uh, directionality. This is infrared is very directional. You would know this line of sight because you when you have to change the channel, you necessarily have to pick up the remote in your hand and point it towards the TV. Why? Infrared needs line of sight. They should see each other for communication. It cannot pass through any objects in between. It's very cheap, easy to build, but the problem is directional. Again, no license is required. I give an example of IRD. IRD port is an example. TV remote control is an example as well. Normally used for communication indoors because it's a very short communication, few meters communication. It does not support outside. Have you seen any infrared being used outside? No, because sun would alter with infrared. Sun shines brightly would alter the infrared signals moving across. This I had drawn, there was this one line of sight. This shows what is line of sight propagation. This is ground width, this is line of sight propagation. And then the earth comes in between and it cannot transmit. This one shows free space loss, I find here. Alpha, I did not get your question. Can you explain what you mean by your question? Rewrite your question. And then in the spectrum, we have the light wave transmission, which is basically unguided optical signaling. Now, with light without, now you'll say, how come I use light here? We use light in fiber. If we use fiber, it's guided. If you do not use fiber, we just use light for communication. It is unguided. Like you might have heard the term Li-Fi. 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 It's, then Wi-Fi, you have Li-Fi. Automatic doors typically would use microwave or typically we use microwave signals. Alpha, that's the answer. If you mean your gate, if you are opening the garage door, it's typically microwaves that are used. Okay. Now, I was talking about the light transmission through unguided media. So Li-Fi as an example, Google Li-Fi and read about it, what it is. And also, it was previously tried that from one building to another building, we send light across, a LAN connected using lasers. A laser was mounted on the rooftop on one side and the uh, detector on the other side. You send the light as beam. It's a unidirectional, and then the detector would find whether it's a 0 or 1. It used to give very good bandwidth but low cost. but it needed a very narrow beam. But the disadvantage was rain, fog, and so on. So it didn't work that well. All right. Now, I believe you would have another class coming up. I would want you to read a little bit about telephone system to get an idea of how PSTN works. I'll just write here PSTN. That stands for Public Switched Telephone Network. You know what are end offices, what are intermediate switching offices, what is a typical circuit route for a medium distance call or a long distance call, the two voltages that are allowed, 5 volt and plus 5 minus 5 volt for digital communication. A little bit about digital communication would also help. I believe you might have studied that because of datacom course. So, mhm, correct. Any questions till now? I will send across one of the sheets. Have a look at it. We'll refer, keep that on your desktop. We'll refer to that again and again to understand that. That would be helpful to us. I think I still have 10 minutes. I'll take that 10 minutes in discussing about transmission impairments. Let me see if I have this slide for transmission impairments. Also, I will send this file of transmission media that might be a bit helpful. I'll share this in the Google Classroom. Okay. So next part is about transmission impairment. For that, I would use the whiteboard. Okay. Topic is transmission impairments. This is the last topic for today. Now, when we see the transmission like analog signaling, it has varying voltage, all right, uh, even with some digital transmission as well. There are some type of impairments that come across. So a transmission line suffers from three major problems. The first problem, yes, I know you can also write. The first problem that we have is attenuation. What is attenuation basically? Attenuation by definition is loss of energy as the signal goes on to propagate. When I said that we have a Cat6 cable which can transmit up to 100 meters, why only 100 meters? Because signal faces certain resistance because of which the signal gets dampened. So this is what we call as attenuation. That is loss of signal as the signal propagates from one place to another. Now, different forms of media has different types of attenuation. Okay, even you talk about the light here. At one point of time, you would need a repeater for a fiber as well. The second is delay distortion. This is the second transmission impairment. This causes incorrect reception. What happens in which some components of one bit may catch up and overtake the slower components. This we know as delay distortion. Yes, I understand you have a class after this. So third one is noise. I'll just end this up. Noise. So what is noise? Noise is basically some extra energy or unwanted energy while you are sending a signal from source to the transmitter. It can be at the source, it can be at the transmitter, it can be in between. Several types of noise is there. For example, thermal noise. What is thermal noise? Thermal noise uh, is caused by random motion of electrons in a wire. This is something that is unavoidable. There is crosstalk. I talked about crosstalk. When you have two wires very close to each other, these two wires, can cause crosstalk, which is caused by basically inductive, I'll write that, coupling. There is impulsive noise as well, which is caused by spikes in the power lines. You get, power spikes that can cause this. All right. This is about some transmission impairments that we come across. I'll end my class here. You'll have some time to join to the other class. Do you have any questions? Any questions?